Okay, let me remind you, we should at this stage have an immediate knowledge of a number is said to be an interior point of a set when there exists delta greater than 0 such that the stick center x radius delta is included in the set. And when that happens, the set's called a neighborhood of the number. And if a set is a neighborhood of every one of its members, then the set is called open, right? What does it take for a set to fail to be open? There must exist at least one member that is not an interior point. By the way, therefore, there must be at least one member. You understand? If there is at least one member of the set that can count in Chinese, then the set is non-empty. Isn't that right? So therefore, the empty set is open. Another open set is the entire number line. Every open interval is an open set. And then I talk to you about closed. When is a set called closed? When its complement is open. So what does it take for a set to be closed? I'm going to write this here. A set S is closed if and only if what? Every member of complement S is an interior point of complement S. Okay? I'm going to say this again in a different color. A set S is closed if and only if for every x in complement S, the number x must be an interior, is what I read. The number x must be an interior point of complement S. That's not what I'm going to write. That would just be repeating the yellow thing, you see? For every x in complement S, I'm going to spell out what it means. There exists, you want to, there's my positive sign, delta, positive, yes, such that the stick center x, radius delta, is included in complement. There's another way of saying it. I'm going to, I've got another color left, so let's say it again. A set S is closed if and only if for every x in complement S, there exists delta greater than 0 such that, I'll copy that far, and I'm going to write this one more time. The assertion that this stick is a subset of complement S is the assertion that this stick does not contain any numbers that belong to S. All the members of that stick have to be where? In complement S, so none of them are in S. So that's there. Here are lots and lots of ways of saying that a set that a set succeeds in being closed. Okay? Okay. Whew. Now, I am coming down to the new stuff. I just wanted to nag you a little bit. I'm going to be talking to you about 3 words. Close, closed, closed, and closure. closed, we've done. Right? I want to tell you what it means, close. Definition of close. Here it is. A number. A number x is said. Do you understand that the words said and say and write and written and call and define are definition words? Every time those words are used, a definition is being made. We define x equals 5. That's a definition. We define W to be the supremum of the given set P. You see? Not, we define x to be a prime number. Garbage. Why? Which prime? You see?
We define x to be the least prime.
That you could do. As long as we agree whether one is prime or not. I don't want to get into that particular. You have enough trouble with the axiom of choice. I want to tell you all, if anybody ever finds, if you follow me through mathematics and you work with me, I'm telling you right now, I am a pro-axiom of choice person. I'm what I call a pro-choice mathematician. I work with choice. If you're one of these intuitionist people, you can go work with somebody else. I work with choice. Can't do without it. Okay? Isn't that right, Nicole? I see she's looking at me, right? Okay. So, all right. Then a number x is said to be, here's the new word, close. Well, close if it's, romantically involved with the set, or what? What is it close? How close is close? A number x is said to be close to a set E. I don't want to use the letter E. I want to use an A. I don't care. All right, E. All right. A number x is said to be close to a set E when something really special happens. When the condition that holds for every delta greater than 0. Not there exists. Look here. My finger up in the air, that unfortunately is not showing in the video. My finger is over there and my other hand is a set. Now if I take an enormous great big delta and I go to the left and right, it's going to hit that set. Isn't that right? There exists delta greater than 0 such that the stick intersects with a given set E. That's dime a dozen. You understand? No. For every delta, even if delta is small, you see? The condition that a number be close to the set means that if you take a stick center x with radius positive, no matter what that positive number is, for every delta greater than 0, even if delta is teeny weeny, the intersection of that stick with E will be non-empty. And I'm going to tell you again in a different color what it means for a number to be close to a set. Give me a moment. I have to finish this thought. A number x is close to a set E if and only if it is impossible to find delta greater than 0 such that the stick intersected with E is empty. Saying that this intersection is always non-empty means that it will never be empty. Are you with me? I'm just chewing on it. I know you got a question. I'll come back. I can't break this. Change color. A number X is close to a set E if and only if, you know what? If and only if it is impossible to find delta greater than 0 such that. There, save my typing. It is impossible to find delta greater than 0 such that this intersection is empty. It's impossible to find delta greater than 0 such that this is included in complement of E. The statement that nobody in here belongs to E is exactly the statement that everybody in here is in complement E. You understand? Saying that X is close to E is exactly the same as saying you cannot possibly find delta greater than 0 for which that intersection is empty. Because what does the yellow definition say? The yellow definition says a number is close to E when every one of these intervals does intersect E. Do you understand? That means you can't find one. It's impossible to find an interval with positive radius around X that fails to intersect with E. You see? You can't find that. Well, let's rewrite it. You cannot, there cannot exist, there is not any delta greater than 0 for which that interval is included in the complement of E. You understand? So I'm hoping that we can now pick up one more. Unfortunately, I'm back to an old color. A number X is close to a set E, and look at this gray. I don't know whether that's gray. It's a sort of strange color. Read this one. A number X is close to a set E if and only if it is impossible to find positive number delta for which this interval is included in there. Impossible. Anybody have a suggestion for me? How could I rewrite that? I'm going to squeeze them for it, and then I'm going to give you a chance. Read this. It is impossible to find delta greater than 0 such that this interval is included here. I'm going to push you here. Yeah, tell me.
If R set minus E is open?
You're too strong. I know what you're thinking. It's not bad. Galen?
Number X is close to a set E if and only if it's possible to find delta greater than 0.
It's impossible. It's impossible.
You can do it with union, can't you?
Union of what?
Well, I'm saying you can do it with union X minus
It's
delta.
impossible to find delta greater than 0 such that this is included. I'm going to come to you 1 second. There was one hand. Yeah?
If and only if the stick is a neighborhood to the complement.
What stick? The stick. No, there isn't a thing called the stick. Mace?
X is not an interior point of the complement?
What were you going to say?
I don't remember. I lost it.
Oh,
Trying to follow this.
I love it. Thus, the existence of delta greater than 0 for which that is included here, isn't that the statement that X is an interior point of that set? Folks, what does it mean when we say, that's why what you said about neighborhood, you were just kind of scratching for it. It wasn't bad. Hers is better, right? What is the definition? What is the statement that X is an interior point of a given set called Charlie? There exists delta greater than 0 such that that stick is included in Charlie. And when I'm saying it does not exist, then I'm saying that the number is, talk to me again, tell me, say it again, Mace. Not an interior point of E. That's it. Terrific. See? Okay. If and only if X fails to be an interior point of complement E. You understand? The numbers that are close to E are the numbers that are not interior points of complement E. Read this. A number X is close to E if it's not far away. Now, what should far away mean? I'm not going to give you a definition of far away. Far away means it's deep inside the complement. Right? That's far away, right? Deep inside means interior point of the complement. You see? So a number X is close to E if and only if X is not interior to the complement of E. The assertion that X is an interior point of that set says what? What does it mean? X is an interior point of Charlie. There does exist delta greater than 0 such that the stick is included in Charlie. And now I'm saying, well, there does not. There is no delta making that happen. That means that's the statement that X fails to be an interior point. Okay. That's very good. Okay, so question still? No? All right, so I'm now going to make some statements. I'm going to tell you, we always have this. Let's talk. Suppose that A is a set of numbers. All our sets are sets of numbers until further notice. I want to tell you why every member of A must be close to A. Isn't that the statement? And I'm going to ask you a question. How do you prove a statement that says every member of A eats chocolate? Every member of A... Let me hear. Suppose X is in A. That's how you do it, right? Now, I'm changing color. What did I do? I meant to do that. I don't know what that other thing was. Okay. Now let's think about close. I need to explain why for every delta greater than 0, I've got all these weird fragments left over from who knows what. I need to explain why for every delta greater than 0, we must have the stick center X radius delta intersected with A not equal to the empty set. Okay? So how do you prove How do you prove a statement that says that for every delta greater than 0, something happens? How do you, to prove for every, suppose what? Suppose a chicken, what? Suppose that delta is greater than 0. Now, the interval, the center x radius delta, contains the number x itself, which happens to belong to A. You notice? Yeah, right. There's something that's in both. And so, at once, this intersection is not empty because I have an example of a number. How do you prove that any set is non-empty? Method of proof that a set is non-empty. Lead a member through the door on a string and say, you want to prove that there's a set of unicorns is non-empty. Here's a unicorn. It bites, don't come too close, or whatever, right? To prove that, so I've given an example of a number that is in that intersection. What happened to the A? Okay. I've given an example, therefore I know that the set is non-empty. Okay? So it's actually a very simple proof, but I used it as a case study in the writing. If you get the writing correct, you will be able to do the mathematics. I want to tell you something. The process of learning the language, the writing in mathematics, it's not any different from any other kind of writing, and in some ways it's easier because the language is very stereotyped and it's very repetitive, and you have to be absolutely reliable. And I'm very careful when I teach you to make sure that we don't use any words that could have more than one meaning. Any words that could be ambiguous, we don't use, so we can relax and we know what we're saying. So I want to prove that every member of a set must be close to the set. You could say, well, if you remember, you're right there. Of course you're going to be close. Well, let's make sure we follow the definition. Suppose that x belongs to A. Now, look at the definition. I need to prove that for every delta greater than 0, something happens. Suppose delta greater than 0. Now we look at the interval center x radius delta, and I'm desperately searching for a point in that interval that belongs to A. I got one. X itself is right there in the middle of that interval, and it belongs to A. Done. You see? Now, warning. It is possible for a number to be close to a set without belonging to the set. It is possible. It happens quite often. I'm going to give you an example in order to show, because it is possible. Do you understand? I'm trying to prove that something exists. I'm trying to prove that there exists a set and a number for which the number is close to the set but not a member. You understand? Here we go. We define let's say example, I prefer, and then say we define. It's nicer. I'll define A to be the interval running from 3 to 5. And I'll define x to be 5. Do you understand that every stick-centered X with a positive radius is going to move? It's going to move to the right a bit. Who cares? It's also going to move to the left, and it's going to slice into that interval. Is it not? There is no question that this number X, we have X belongs to A bar, there, right? But we do not have X in A. In other words, X is an A bar slash A, because X is not in that interval. You understand? Okay.
So the supremum and
No.
infimum are going to be part of the closure.
Uh,
Or going to be
I think that's going to be one of our exercises. An upper bound of a set is close to the set if and only if it is the supremum. I haven't got time to do that one right at this moment. Okay. I want to remind you, though, that last time we proved that a non-empty closed bounded set, bounded above set, always has a very special kind of supremum. Supremum belongs, it is a maximum, biggest member. I'm just reminding you, I left it in here to tease you. Okay? I'm just reminding you. I might possibly review this. I've left it in here with a possible view to reviewing it because I don't trust you. I don't know whether you've done your homework. You're supposed to have written this out 10 times between last time and today. 9 times would do for some people. The rest have to do it 10 times. Okay. Now, I want to talk to you about, I can't find it. Here. Close in terms of neighborhood. I may come back there. I may relent and come back and give you a review of that. I'm going to tell you that the following conditions are equivalent to one another. I'll call them 1 and 2. I think it'll be easier to state 1 and 2 if I pose my symbols first. For a given number X and a given set S. Let's call it E. Okay. 1. The number X is close to the set E. 2. You say, well, I've given you half a dozen interconnections that are the same as saying a number is close. Got another one for you. Am I repeating myself? I hope so. For every, okay, what does the definition say? The number X is close to the set E. What does that say? For every positive number delta, the stick center X radius delta intersects with E. The intersection is non-empty, right? Okay, for every neighborhood U of X, the intersection of U with E is non-empty. These are the 2 conditions. And we're going to prove. So here is my heading. We're going to have the proof that condition 1 implies condition 2. Listen to me. The only time I permit my students to use an implication sign, or the word implies, or the only time I encourage you to use if-then statements, is in a heading. It is highly dangerous leading to hard problems, bad writing, and general mess, to use implications and if-then statements in your actual mathematical writing. It is a sign of bad writing. Don't do it. And if you teach mathematics, don't do it on the blackboard. It is not proper practice. Are you hearing me? But in a heading, where this is an if-then statement, that if condition 1 holds, then condition 2 holds. Do you understand? That's what this says. And now we're going to do that proof. How do you prove that condition 1 implies condition 2? We assume that condition, with a capital C or a small c, I don't know. We assume that condition 1 is true. You understand? Our job is now to prove condition 2. Okay, so what is it that I've assumed? I have effectively assumed that for every positive number, delta, the delta stick, the stick center x radius delta, intersects with E. I wish to prove that for every neighborhood U of X, U intersects with E. So how do you prove that something happens for every neighborhood U of X?
Suppose U is a neighborhood of X.
Yeah, if you want to prove that something happens for every neighborhood U of X, you say suppose that U is a neighborhood of X, right? You want to prove that every chicken has feathers. Suppose that U is a chicken. Okay? All right. Suppose that U is a neighborhood of X. Now ask yourself, what does that mean? What does it mean when you know that U is a neighborhood of X? Or alternatively, X is an what? Interior. What does that mean? What does the definition say? I'm not asking you to be smart. I'm asking you to quote the definition. X is an interior point of view. You should be like reciting in a kindergarten class. X is an interior point of view. What does that say? There exists delta. An inability to answer me has nothing to do with how good you are at math, or how hard the course is, or I'm good or I'm bad, or you're good or you're bad. It's all irrelevant. It's only a matter whether you decided to learn the definition. The statement that X is an interior point of view, the statement that U is a neighborhood of X says what? There exists, blah, 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 right? When something exists, what do you say? Choose. You see, just follow the mantra. Choose what? Choose. What is it that exists? Some delta, right? Choose delta greater than 0 such that what? Such that, okay, we're making the statement that U is a neighborhood of X, such that this stick is a subset of U, right? Okay, well, let me tell you something. From condition 1, we know that this stick intersected with, what's it called? E, is non-empty. Isn't that right? And therefore the bigger set intersects with E, isn't it, right? And so the U intersected with E is non-empty because all you have to do is look at a number in there. It belongs to that stick. It certainly belongs to U and to E. Okay? This is the more difficult proof. We're now going to do the easy way. We're going to do proof that condition 2 implies condition 1. And I want to emphasize to you, if you make this organized, make it absolutely plain which way you're doing. When you want to prove that two conditions are equivalent to one another, it's an if and only if condition. You are being asked to write two proofs. Be absolutely clear which proof you are writing. Make it absolutely clear what we are assuming and what we are proving. Otherwise, you can't do this stuff. I'll get lost. Got more experience than you, I'll get lost. So we assume, well, you want to prove that condition 2 implies condition 1? We assume condition 2. See? What is it that we've assumed? We've assumed that for every neighborhood u of x, blah, blah, blah. Okay? We wish to prove condition 1. What is the statement of condition 1? Condition 1 says, for, next word, for every, look at condition 1, definition of close. No, condition 1, close. Look at the definition of close. For every delta greater than 0. So we want to, I would even write this in that field. We want, this is to help you see what to do. We want to prove that that for every delta greater than 0, we have this stick intersected with, what's the set called? E is unequal to the empty set. I'm just spelling that out, and I'm coming back to our main color now. All right? How do you prove that something happens for every delta greater than 0? Suppose what? Suppose that delta is greater than 0. End of sentence. Okay? Since this stick is a neighborhood of x, that we know, we deduce from condition 2 that this stick intersected with what's the set called? E is unequal to the empty. There you are. That's the easy direction. The harder direction was 1 implies 2, took 4 lines. Easier direction took 2 lines. So therefore this direction is twice as hard as this one. So I'll tell you a story to give you a moment to breathe. When I wrote the first edition of this book for the Random House Publishing Company, I submitted my manuscript to the editor, Richard Wallace. Wallace spelt as in Wallace's formula, but he's not a mathematician. He's actually a music expert, but he was the math editor in those days. So that's neither here nor there. So when I submitted, I was very proud of the fact that I was including the first ever proof at elementary level of the Osceola bounded convergence theorem. I will say something to some of you one day about this. It is a very, very beautiful, powerful, useful fact in mathematical analysis, and everybody believed that it was too hard to do in an elementary course until I found an easy proof and published it in the monthly. And my book was the first book ever to have this, and made all kinds of other things much easier than ever before. I was so proud of this. So one of the reviewers writes, he says, I'm sorry to see that Lewin's proof of the Osceola bounded convergence theorem is twice as hard as Bartle's proof. I was devastated. Bartle's book had it? I published this in the monthly. It was regarded as new. What do you mean it's in Bartle's book? I called the editor and I said, find out from the reviewer. I don't know who the reviewer is, you understand? I'm a real idiot, I can tell you. I said, find out from the reviewer. I can't find it in Bartle's book, for good reason, I think. But what page? he gets back to me, page 277 or something. So I open up Bartle's book and to 277, and there's absolutely nothing even remotely to do with it. So I didn't know whether to feel relieved or what. And I look, and I've got the second edition of Bartle's book. And so I immediately checked the books in print and literature. I discovered that the edition of Bartle's book that I had was the latest. So I wrote back to the editor and said, what edition is he using? Comes back, it's the first edition. So I had to, like pulling teeth, I had to find him, managed to borrow a first edition of Bartle's book. I managed to get hold of one. And there on page 277, I see Zeeler bounded convergence theorem, and the proof is half the length of mine. And I was too upset to even try to read it. I mean, I'd been commended. I gave this presentation to something like 250 people in a big at a meeting in New Orleans. I had a who's who of American mathematics in that hall. It was a great moment for me. What? And it was in his textbook. So I telephoned Bartle. And I was actually quite upset. I said, why? Why did you leave that theorem out of your second edition? How are we to know that this appeared? Why did you leave it out? He says, you haven't tried to read my proof, I can see. I said, no, well, I haven't. He said, don't bother. It's, the word he used was a bit vulgar. It was to mean that something is no good, right? Professors have to walk on eggshells. So it's the kind of language professors aren't allowed to use. But he said, it's one of my embarrassments. The proof was complete nonsense. And so I was the first, actually. And anyway, but the reviewer looked, mine was this length, his was this length, therefore mine was twice as hard. But his didn't work. To write a proof that didn't work, I could also have made it shorter. So anyway, okay. Well, we've done this. How are we going? Any questions? All right. Well, I want to do this one now. No, I think I better do this. I'm feeling a little bit worried that maybe I need to do this one again. I shouldn't, actually. I did it with you last time. Twice, actually. I'm going to do it again. I'm scared. A non-empty closed set bounded above must have a greatest member. What do you need to do to prove that a set has a greatest member? You've got to prove that it's got a supremum and that the supremum belongs. Well, there's not much to get the supremum. The set is non-empty and bounded above. See? So I want to tell you that our task, I'll write this, our task is to explain why sup H, the set's called H, must belong to H. I'm just stating the task. You understand? I'm going to do it by contradiction, and I did this last time. We assume, to obtain a contradiction, that this number fails to belong to H. I'm pulling the sketch down to here. Using the fact that where did I say that the supremum is called W? I said so here. I thought I'd forgotten. Because the last time I wrote that, we were giving the name W to the supremum. Otherwise, looking and say, what the hell is W? See? Okay. To obtain a contradiction, we are assuming that this number W does not belong to H. Using the fact that W belongs to the open set. Trying to get back here. If you don't belong to H, you belong to the complement. Using the right, we choose delta greater than, well, when a number belongs to an open set, what is it that we know? What does open mean? Every member of the set is an right, so X is an interior point of that set, so therefore what? There exists, well, I've said choose. Choose delta greater than 0 such that this stick is included in complement. Where am I? Complement H. See? Yes? Okay. Using the fact that X. All right. Now, where can numbers in H belong? No member of H can be greater than W minus delta. Let me tell you why, but I'm not giving you as much detail as I gave you last time. If a number is greater than W minus delta, either it's in the red stick or it's not. Numbers in the red stick are never in H because they've got to be where? Complement H. And a number above W minus delta that's not in the red stick is terribly big. It's above there. And that's too high to belong to H because W is an upper bound of H. You will find it in the lecture from last time. A number greater than W minus delta can never belong to H. Because if that number is in the red interval, the stick, how come there's an X here? How come you let me put an X? It's got to be a W. If the number is in that stick, it's got to be in the complement H. So therefore, no members of H are in the red stick, right? But if a number is greater than W minus delta and it's not in the red stick, it's got to be at least that high. And that's above W, which is a known upper bound of H, and therefore, again, the number can't be in H. Do you understand? So I'm going to make a statement to you. For every X in H, we must have X less than or equal to W minus delta. Is that clear? We have shown that W minus delta is an upper bound of H, because every member of H is less than or equal to it. And this is impossible, because W minus delta is less than the least upper bound. It violates the BMW argument. If you're less than the least upper bound, you are not an upper bound, you see? Okay. Right, now let's do this one. Given two sets A and B, with A a subset of B, I want to prove that A bar, have I given you the definition of A bar? Did I? I forgot to give it to you. What color should I choose? The set of those numbers, of all numbers, that are close to a set A is written as A bar. I forgot to tell you that. So when I told you here, this, you should have objected. You should have said, what do you mean by a bar? But you say, well, I know because I read it in the book. Yeah, but I should have told you. This means the set of numbers that are close to A. I should spell it all out. Okay.
And also for the way up there on the blue line, is that supposed to say not equal to? I'm sorry.
Where, what?
Scroll up 2 more lines, I believe. One more.
Where? Where are we looking? What color is it?
It was a blue line, but it wasn't that blue.
Blue.
Yeah, it was in close. Whenever we were talking about close. If a number x is close to a set.
Is this?
Right there. Is that blue line supposed to say not equal to at the very end of the intersection?
Over there?
Okay, yes, sir. Is that supposed to say not equal to or equal to? I'm just making sure.
A number x is close to a set E if and only if it is impossible for such an intersection to be empty. See? Impossible to find delta greater than 0 for which the intersection is empty. That means that the intersection has always got to be non-empty. Okay? Always non-empty means never empty. So, okay? It was worth looking. Right, I want to do this. Given 2 sets A and B, and A is a subset of B, I want to prove that A bar is a subset of B bar. Are you ready? How do you prove that A bar is a subset of B bar? Suppose. How do you prove that every member of A bar has got to eat ice cream? Suppose that X belongs to A bar. Okay? All right. I'm going to change color. Whoops. Lost my bar. Come back. I'm going to change color and I'm going to tell you what I want to do. I want to show that X has to belong to B bar. Okay? I'm going to spell this out again. I do this all the time when I'm trying to do math. I always ask myself, what do I want? I can't see how to do this stupid proof. I'm not smart enough. Well, what is it that I want? And then I ask, what is it that I've got? And what do I want? And what have I got? And I write them over and over again in different ways. And sometimes I see the connection. And more often than not, I don't, and I give up in disgust. That's the name of the game in mathematics. Most of the time when I try to do something, I don't succeed. Every now and then I do, and feel on top of the world for a while. Okay, so anyway, I want to show that for every delta greater than 0, the stick center X radius delta intersected with B is non-empty. Isn't that right? Okay? Right. How do you prove that something happens for every delta greater than 0? What am I hearing? Suppose what? Suppose that delta is greater than 0. Okay? Well, we do have the stick center X radius delta intersected with A is non-empty. That we know, right? and so the stick center X radius delta intersected with B can't be empty either, because A is a subset of B. You see, it's that simple. Okay? If A is a subset of B, then A bar must be a subset of B bar. I hope you don't think I'm going to do that. We've already done this today, haven't we? The closure of a set is always closed. I'm almost done with what we're doing today. Suppose that S is a set of numbers. We want to prove that S bar, I don't like calling it S. I'm going to use an A. The bar doesn't look nice on an S. That's what I've been trying to avoid. It's hard to type a bar over the letter S. It's a screen problem. If I print with Scientific Workplace, the high quality print there, it looks beautiful. But on screen, it doesn't. So, okay. This one doesn't look bad, but it's a big one, you see. Okay. Suppose that A is a set of numbers. We want to prove that A bar is closed. Do you understand? Now, we have seen that haven't I told you that a number is close to a set exactly when it's not an interior point of the complement? Actually, I didn't tell you that. Mace told you. You say, but you don't believe her, you believe me. She's reliable. We saw, I wormed it out of you. A number is close to a set when it fails to be interior to the complement. So a number is not close to a set when it is interior to the... Yes? Which numbers are close to a set? Those that are not interior points of the complement. Okay? Which numbers are not close to a set? Those are the numbers that are interior to the complement. A point is close to a set S if and only if the point fails to be an interior point of the complement. So a number will not be close to the set when it is an interior point of the complement. The number is close to the set when it is not interior to the complement. Suppose I tell you, suppose I say, a person in this room likes chocolates if and only if that person is not male. Then I would say a person in the room doesn't like chocolates if and only if the person is male. Yes? Now this statement might be true or false. It would be true if all the females like chocolates and none of the males. Males prefer chips or something. Okay? I'm not trying to stereotype people. Don't get me into trouble. You'll bring the so-called diversity people on my shoulders. I know I'm not supposed to talk politics, but I've run head on head with these people. I can tell you that the people who talk about diversity on this campus would not recognize diversity if it were handed to them on a plate with watercress around it. And that goes for all of them in that office and all these. And the more they talk about diversity, the less committed they are to it. Anyway, I could a tale unfold whose lightest word would harrow up thy soul. That's all I can say. Down all the way to the fretful porpentine. But leaving that aside, let's come back. This was give you a rest. The points that are close to a set are the points that are not interior to the complement. The points that are not close to a set, the complement of A bar is the set of interior points of the complement. Yes? Now, we know that the set of interior points of this set, or in fact any set, must be open. Isn't that right? I did it with you when we studied interior points. One of the things that we saw, and you have to turn back, I explained to you why the set of interior points of a set always has to be open. I did it. The set R/A bar, the complement of A bar, is a known open set. Since the complement of A bar is open, it's the set of interior points of that. The set of interior points must be open. Since that is open, the set A bar must be closed. Do you understand? The set, and so where do we have this? It's not here. It's in the lecture before. I said, I gave you the definition of an interior point. And one of the things that we saw there was that the set of interior points of a set must be open. So, okay, folks, here is a set called A. The complement of A bar, meaning what? That's the set of points that are not close to A. The complement of A bar is the set of interior points of that. The set of interior points of any set is always open. Therefore, this set must be open. Therefore, A bar must be closed. The text also shows a direct proof, not using the fact, not going back to interior points. It shows a direct proof. You can look at it if you like, or use this one if you like. But I do have a direct proof explaining why, if A is any set, then A bar is closed. But I decided to do it this way. I said, in a previous life, last Wednesday, I said, if you take any set, and you look at the set of all interior points, that's always open. Now, here's a set called A. Complement A bar, that's the set of numbers not close to A. That's exactly, those numbers that are not close to A are exactly the numbers that are interior to complement A. The set of all interior points of a set is always open. That set is open. Therefore, A bar is closed. That's how it works. Okay? That's as far as we're going. So I know that I'm basically pushing you and pushing you. To some extent I review, to some extent I give you new statements. The learning will never be in this room. When I was an undergraduate student, I don't believe there was ever a time that I followed a lecture. I would leave the lecture room, hopefully with notes that on which I could rely, sometimes not, and I would try to piece the whole thing together myself and say it myself and write it out. That's what you have to do. The only difference is you will have notes on which you can rely. You have everything laid out for you. Rewrite and rewrite and rewrite. And when you're absolutely positive that you've written it out enough times, write it one more time.
Just to ensure that it wasn't
Yeah. So that's the story, and I'm no longer